All right, so moving along here in unit 3, on to lesson 2, we are done, although they're not going to go away, but we are done the exponential functions portion, at least where we're mostly focused on just the exponentials. As you'll see, exponents and logarithms are very closely linked, so it's not like we're going to stop thinking about about exponential relationships. In fact, we're just going to be thinking about them, but kind of in a different way here with our logarithms. As you will see, logarithms and exponentials are really kind of two sides of the same coin. It's hard to talk about one without talking about the other. So, as always, here's a little checklist, right? The important skills and ideas that we hope to have down by the end of this lesson. So you can use that to check in with yourself afterwards. But let's jump right in. All right, so a logarithm. This is kind of one of those exciting days in math where it's actually something that's pretty much entirely new. Now, I say that, but honestly, like I said, logarithms are just another way of thinking about exponential relationships, so it's not as new as it seems at first, but they do look pretty different, right? Most of the stuff we've done in Math 30 so far, you've seen it before. We're kind of just taking it a step further. Logs really are kind of a new thing. We've never written a logarithm before. So kind of cool, okay? But let's get some background so we can understand why logarithms are even a thing in the first place. Okay, so you know a lot about inverse operations. You use them all the time. These are the operations that can undo each other, right? So for example, you know how to undo all of the operations that are being performed on X in all of these situations here. You're using inverse operations in all of them. You're doing the opposite in order to undo whatever's happening to X, in order to solve for X, right? So for example, subtraction is the inverse operation of addition. Subtracting something undoes adding something. So X plus 1 equals 5. How do we solve for X? Well, it's having 1 added to it, so we need to undo that. The opposite of adding 1 is subtracting 1. The inverse operation of addition is subtraction, right? So adding 1 and subtracting 1 undo each other. They cancel each other out, and we just have to do that to both sides, right? But the point here is that the inverse operation of addition is subtraction. So the fact that X is having 1 added to it, we can undo by subtracting 1 from that, okay? Similarly, addition is the inverse operation of subtraction. So if we had X minus 1 equals 5, how do we undo the fact that we're subtracting 1 from X? We add 1. Addition and subtraction are inverse operations, so they kind of undo each other. X is no longer having 1 subtracted, it's now just X. And by doing it to both sides, we've solved for X. Okay? Division undoes multiplication. Division is the inverse operation of multiplication. So X is being multiplied by 2. How do we undo that? We divide by 2 to solve for X. Multiplication, inverse operation of division. So look here, X is being divided by 2. We can undo that by multiplying by 2. And we do that to both sides in order to solve for X, right? This is just some algebra skills that you've had in your back pocket basically since you started high school math, even junior high math, right? Square rooting is the inverse operation of squaring. Just another example of an inverse operation that you know and love already, right? X is being squared here. To undo that, we square root. We have to do it to both sides. That lets us solve for X. Squaring is the inverse operation of square rooting. So we're taking the square root of X. We can undo that by squaring, right? Squaring and square rooting cancel each other out, leaving us with just X. We are undoing the operation that's being performed on X in order to isolate X, right? We want to undo the things that are happening to it. But what about in this situation, right? If I gave you all of these, I could have given you these in grade 9 and you should have been able to solve for them, right? What about this though? 5 to the power of X equals 100. You know the idea behind figuring out what X is. We need to undo the operations happening to X to solve for it. Except, what is the opposite of something being raised to the power of X? It's not X to the power of something. We know we could use a root to undo that. This is something to the power of X. We don't have an inverse operation yet for exponentiation. That's what we call this. X is being exponentiated because it's the exponent. So we don't yet know the inverse operation of exponentiation. That's what we're going to start learning in this lesson. The inverse function of an exponential function is what we call a logarithm. So by using logarithms, once we understand them, applying them to both sides is going to allow us to find x in this example. We're not quite going to get there today. I mean, we kind of will, but we'll mostly start solving these equations using logarithms tomorrow. Today's mostly about exploring what logarithms are really saying, okay? But that's kind of the goal here. This is, I said at the beginning, why do logarithms even exist? This is part of it. It allows us to solve for x in a situation like this, right? Here we knew we had to subtract 1 from both sides. By the end of our talk about logarithms, either this lesson or next lesson, we'll start to see why taking the logarithm of both sides will allow us to undo the fact that 5 is being raised to the power of x and solve for x, just like we could have done with all of these. Okay, so just like we did with, subtracting something from both sides when something's being added, or dividing both sides when something's being multiplied, or square rooting both sides when something's being squared, etc. Okay, now the idea of a logarithm is going to seem very new to you at first, but I promise they're actually just another way of representing a relationship that you are very familiar with, namely exponential functions, or exponential relationships, I should say. So we're going to ease ourselves in a bit here by just getting a basic grasp of what a log actually tells you. And here it is. It's not that fancy. Logarithms simply provide another way of writing exponential relationships. Okay, so take a look here. These are saying the exact same thing. This says that a equals b to the power of x, and so does this once we know how to read it. Okay, so you can take a look down here. We'll start getting into it in a second, but I just want to introduce you to it first. This is just another way of representing an exponential relationship. You might be saying, come on, why do we need another way? It's just getting confusing now, 2 ways to say the same thing. I promise as we go, you'll start to see, oh yeah, this is handy because now I can move that x out of an exponent if I need to solve for it. Okay, that's why these are powerful, right? You can see there, x is out of the exponent if we start thinking about it this way, and that can be very handy. Okay, so taking a look here, this is it. Exponential form of a relationship, we say a equals b to the power of x, and then in the logarithmic form of the same relationship, that's the key idea, nothing different here, it's the same relationship, we could write this as, we would say out loud, log base b of a equals x. So log base b of a is equal to x. Here is what we are saying, and here's how to read a logarithmic expression, okay? It's just taking an exponential relationship and it represents it like this. So we sometimes talk about, a backwards C. You sometimes hear people say, it's just saying start from the base. All it's saying is that this base to the power of whatever this is equal to equals this, what we call the argument. So this is really it. Whenever you're looking at a log, I always kind of say in my head, I say this to the power of this equals this. And I kind of just do that little, backwards C, because you kind of make that shape, right? Like a backwards C. And that's really all it's saying. So b to the power of x equals a. Just kind of peeking ahead a bit, all this is saying is that 2 to the power of 3 equals 8, which is true, right? 2 cubed does equal 8. And that's all we're doing. We're representing an exponential relationship in a different way. I know it seems weird at first, okay, but I promise there's a lot of good math that representing things this way can allow us to do. Okay, so again, b to the power of x equals a. Notice, right? Same thing. B to the power of x equals a. B to the power of x equals a. See what I mean? It's the same relationship. B to the power of x equals a. B to the power of x equals a. Okay, just some terminology. B is what we call the base of the logarithm. Notice how I said log base b, right? Because b is our base. This would be log base 2. This would be log base 4. Okay. And one nice way to remember that is that that's the base in the exponential it represents, right? We have the base of an exponential and the exponent of an exponential. So the nice thing here is the base of the exponential is the same thing as the base of the logarithm. A is known as the argument of the logarithm, it's essentially what we're taking the log of. So you sometimes say log base b of a. Like you could put brackets in here, and that's what you're doing. You're taking log base b of a, okay? Note that neither the base nor the argument can be negative in a logarithm. The base also cannot be 0 or 1. We're going to just put that on the back shelf for a second so we can spend some time getting comfortable with logs, okay? But I promise we'll circle back to why that makes sense, why the argument and the base could not be negative, and also why our base cannot be 0 or 1. But first, let's just get comfortable with some logs. I know they're a little weird at first. I know it takes some getting used to, but let's just switch between logarithmic and exponential form so we can really get that relationship down. Because once you understand this, there's not that much more to think about. I mean, I shouldn't say that. There is stuff to think about with logs, obviously, but that's all it's doing, right? Once we can accept that it's just saying this to the power of this equals this, a log doesn't become so weird and mysterious. It's just another way of representing an exponential relationship. Let's try switching between them. All right, so first when I went ahead and wrote this in for this, okay? This is all we got to do. We got to read this correctly. So this to the power of this equals this. So this is just saying 2 to the power of 3, sorry, pen wasn't working, equals 8, right? Which is totally true. 2 cubed does equal 8, right? This to the power of this equals this. 2 to the power of 3 equals 8. Okay, let's try this one out. So 4 is our base, right? What we're saying here is that 4. So this to the power of this. So to the power of 3 over 2 equals the argument. 4 to the power of 3 over 2 equals 8. Which might not be as obviously true, but if you remember that, from our exponent laws and just thinking about what this is saying, this is really, I mean, you could think of it if you like as this. So let's just pause there. This is it in its exponential form. Let me now just convince you that this really is true, right? This is the same as, for example, 4 cubed times 1/2, right? That's 4 to the power of 3 over 2. And so we could think of this as 4 cubed to the power of 1/2. And to the power of 1/2, that's just a square root. So this is just the square root of 4 cubed. And 4 cubed is 4 times 4 is 64. And sure enough, the square root of 64 is 8. So it works. Okay. All right. Let's try this one here. Now, notice we can't quite say the sentence. So I sometimes tell students this. If you can't say the sentence without leaving something out, you're not quite ready to convert forms, right? So what I mean by that is, by the sentence, I mean this to the power of this equals this, right? So notice there's a 2 here. Now watch, as I say this, am I including the 2? Ready? 9 to the power of 1 equals 3. Hang on a sec, I never used that 2. The 2 is clearly important. It matters here, right? So I can't just leave it out. What's more, you can tell something's wrong because 9 to the power of 1 does not equal 3. 9 to the power of 1 would equal 9. So notice, right, this sentence, this to the power of this equals this, we're not leaving anything out when we do it here. We weren't leaving anything out when we did it here. We weren't leaving anything out, right? 2 to the power of 3 equals 8. When I try to do it here, if I'm leaving it in this form, I have 9 to the power of 1 equals 3. But what about this 2? It never came into the equation at all. So that's a little hint, right? A little clue. Okay, we've got to first rewrite it so it actually looks like something where we can say that sentence. This to the power of this equals this, right? Well, that's going to be pretty quick. Let me just isolate the log, right? We're supposed to have log base b of a equals x. I don't have that. I have 2 log base b of x equals, 2 log base b of a equals x. So how do I do that? Well, 2 is being multiplied by this log. Let me divide 2 by both sides. Inverse operation. So now we've got log base 9 of 3 equals 1/2. Now, Can I say the sentence without, leaving anything out? 9 to the power of 1/2 equals 3. I can, right? So the exponential form of this is just 9 to the power of 1/2 equals 3, which is true because 9 to the power of 1/2, that is this logarithmic relationship in its exponential form. But 9 to the power of 1/2, we know that's just the square root of 9, which is 3, right? It works. Okay. So in this example, we're now given the exponential form and we're asked to write it in its logarithmic form. Again, that's all we're doing here, right? It's just different forms of the same relationship. This was saying the exact same thing as this, okay? So let's try this now. Let's go the other way. I just kind of copied and pasted that little, the sentence, the backward C type thing here. So we have 3 to the power of 3 equals 27. So to write this as a logarithm, again, this to the power of this equals this. So here we go. We need to make the base of our logarithm is the same as the base of the exponential. So this is going to be log base 3, okay? And what are we saying here? We're saying 3 to the power of 3 equals 27. So 3 to the power of 3 equals 27, right? Equals 27. Okay, and we can always just double check our work. Did we say what we wanted to say? This to the power of this equals this? Yeah, 3 to the power of 3 equals 27. That's what we were trying to say, and that's true. 3 cubed does equal 27. So there we go, right? We can kind of do that, like I said, backwards C. 3 to the power of 3, sure enough, equals 27. We got it. The arrows obviously aren't actually part of it, but just showing you the little move we make. Okay, 50 equals 3 to the power of m. Same idea. They're trying to throw us off a bit here by switching left and right side compared to how we might normally look at it. But 3 to the power of m equals 50. So log base 3, okay, 3 to the power of m equals 50. Log base 3 of 50 must be equal to m. Do you see what I mean? Once we start learning how to actually calculate and evaluate logs, see how this is powerful? We didn't know what m was before. Now we know m is just equal to log base 3 of 50. And I know you might not know how to actually calculate that, but that is just a number. Log base 3 of 50 is just a number. So we've now solved for m, right? That is why we're choosing to represent these in logarithmic form sometimes, or at least it's part of the reason. Logs can be pretty powerful for a lot of reasons, but this is one of them, right? No way to solve for m here. Now we know what m is equal to. M is equal to log base 3 of 50. What log base 3 of 50 actually is equivalent to, we'll learn how to do as we go. Okay, let's try one more here. X equals 4 times 10 to the 3.5. Now again here, notice, you can't quite say the sentence, right? We could say 10 to the power of 3.5 equals x, but what about the 4? We're leaving that out, right? This to the power of this equals this leaves out the 4. That's an important part of the equation. So how could we fix that? Well, if we divide both sides by 4, let's see if now things are a little bit better. We've got x over 4 equals 10 to the power of 3.5. And now can we kind of, say that sentence without ignoring anything? 10 to the power of 3.5 equals x over 4. Hey, that sounds like we're ready to write a logarithmic form of this exponential, right? We could say log base 10, okay, 10 to the power of 3.5, so 10 to the power of 3.5 equals, what does it equal? It equals x over 4. Nothing wrong with that. That can be the argument of our logarithm. It can be a fraction. I might include some brackets there just to keep things a little bit neater. So all we're saying is that log base 10 of x over 4 equals 3.5. So 10 to the power of 3.5 equals x over 4. 10 to the power of 3.5 equals x over 4. That's exactly what we were trying to say. Okay, and that's all a logarithm really does. It represents an exponential relationship in a slightly different way, that can be very useful, as we will see as we go on. So let's pause right here. Go ahead and try out some of these practice ones. We want to be really comfortable with this relationship, what a log is telling you about an exponential and what an exponential tells you about its logarithmic form. So take some time to practice it and really get that down, because we're going to use it a lot for the next 2 lessons, okay? So give these a shot at the very least. If you're still like, ooh, I could use a little more practice with this probably to be really comfortable, then it's worth, try BCD or 3BCD. But at the very least, do this one while it's fresh in your brain, and then we'll move on. All right, so just an important note before we go any further. That's about logarithms with a base of 10. We call them common logarithms. The reason they're common is that we have a base 10 number system, right? What I mean by that is you go like 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you kind of reset and go 10. And then you go 10 and 1, 10 and 2, more commonly called 11, 12, right? 13, 14, 15, 16, 17, 18, 19, and then you reset 20, right? What we're always doing is we're basically counting out 0 to 9, and then we start a new 10, right? 9 becomes 10, 19 becomes 20, 29 becomes 30. So that's why these are common logs, is because our number system is kind of based around the number 10, right? You almost reset your digits. We have 10 digits, 0 to 9, and you reset, you need another thing when you get to 9, right? So because our number is based on 10, our number system, is base 10. These pop up a lot where we want to think about powers of 10. So we call them common logarithms. Because they're common, they're so common, 10 is the assumed base if no base is shown. So for example, it's not wrong to include the 10, don't get me wrong, but you'll often see it left out because it's common. It's just assumed. So log base 10 of 2 equals 100, which is true because 10, wait, this is not true. I gotta fix that. That's a mistake. That's wrong. 10 to the power of 100 is not 2. Do you see that? How should I fix this? Let's pretend I was testing you, and not that I just made a mistake there when typing the notes. I could fix this by saying 10 to the power of 2 equals 100. I gotta fix that in the notes. Okay, 10 to the power of 2 equals 100. There we go. Fix this one while I'm at it. Okay. Now it's a little crowded looking. Sorry about that. Okay, but back to the point of common logs. 10 to the power of 2 equals 100. So we could say log base 10 of 100 equals 2, but we could actually also just write it as log 100. Leaving out the base means we are assuming it to be 10. So anyone who reads this is going to think we mean there's a 10 there, a little invisible 10. Okay? It's just like how, when you take a square root, you don't need to put in the 2 for the index, right? If you're taking a cube root, you've got to put in the 3 there. But if you're just taking a square root, you could put in the 2, but if you don't, everyone's still going to know what you mean. They're still going to know you mean the square root of 4, right? You could put in the 2, but you don't have to. It's assumed to be an index of 2 if nothing's put there. Same idea here. You could put in the 10, it's not wrong, but if you don't put in the 10, everyone will still know what you mean. So if you don't mean 10, you have to include it, right? If you want log base 3, for example, you need to make sure you put that 3. If you just leave it out, people are going to think you mean 10, right? If you want to take the cube root of 4, you can't say that because people are going to think you mean the square root of 4. You need to include the 3. Same idea here, except with logs and with base 10. All right, so now it wants us to solve for x in each of the following by isolating the log. That's often a good idea with these, not always, but often it can be pretty handy to first isolate the log, because once you've isolated the log, you can say that sentence that I was talking about, right? You can say this to the power of this equals this without leaving anything out. So we're going to isolate the log and then convert forms. So see what I mean? We couldn't say the sentence here. 5 to the power of 6 equals x, but what about the 2? We're just ignoring that. So how can I fix that? Isolate the log, right? So let's divide both sides by 2, since 2 is being multiplied by our log. And that's going to give us log base 5 of x equals 6 over 2 is just 3. Okay, and now we can say the sentence without ignoring anything. 5 to the power of 3 equals x. So we isolated the log, now we're going to do the converting forms. So we're in logarithmic form, let's convert to exponential form. 5 to the power of 3 equals x. This to the power of this equals this. 5 to the power of 3 equals x. So x is just 5 cubed. What's 5 cubed? 5 times 5 times 5? That's 125. So x is just 125. There we go. We solved for x by isolating the log and then converting forms. Okay, let's look at B here. Similar problem, right? We can't really say the sentence yet. X to the power of 4 equals 36, but that's not the whole story. What about the plus 2, right? So first, isolate the log so that we can actually properly look at the relationship here, the exponential relationship that this logarithmic form implies. So I'm going to subtract 2 from both sides. That's going to give me log base x of 36 equals 4 minus 2 is just 2. And here we go. Now I can say x to the power of 2 equals 36, right? That's all this is saying. Now I can see that. X to the power of 2 equals 36. So x squared equals 36. I mean, we could square root both sides now to solve for what x actually is. And we get that x equals, and you wouldn't be wrong to say, okay, if x squared is 36, then x could be plus minus 6, right? The square root of 36 is 6 or negative 6, because 6 squared is 36, but so is negative 6 squared. However, don't forget something, okay? Can we have a negative base, right? I know I've just kind of told you that for now. I promise we'll think about it in a second, why it makes sense, but we can't, right? So, but can't have base less than 0 in our logarithm. Okay, so we have to reject that negative, right? It's what we would call an extraneous solution. Means that it's valid, sorry, actually means it's not valid, but not because we made a mistake in finding it, just because other reasons have to cause us to reject it, right? We can't have log base negative 6. Doesn't work out. Again, because then we'd have negative 6 to the power of stuff, which gets messy when we change our variables. We'll talk about that. Okay, here's one. Log x equals 3. Oh, looks like they forgot the base. Or did they? If there's no base, what do we assume it to be? It's 10, right? It's not really, we're not assuming, that's just how it works. If there's no base written in there, it's base 10. Same way, if there's no index written in a root, it's a square root, okay? So there's a base of 10 here. So what is this actually saying? It's saying that 10, right? This 10 to the power of 3, so to the power of 3 equals the argument. So 10 to the power of 3 equals x. This to the power of this equals this. So 10 to the power of 3 equals x. And therefore, x is just 10 cubed. So x is just 10 times 10 times 10, or 1,000. And there we go. We've solved some logarithmic equations for x just by isolating the x and then changing form to exponential form. Okay. So let's actually look now at evaluating some logarithms, figuring out what they're actually equal to, right? Because we can do that with exponentials. We do it all the time. In fact, we did it here. 5 to the power of 3. Sorry, this is not working. There we go. 5 to the power of 3 is just 125, right? Can we do that with exponentials? So don't forget, by definition, log base b of x means b to what power equals x, right? And that is what log base b of x is equal to, right? If we had log base b of x equals stuff, then really what we're saying is that log base b of x is just equal to the exponent we would need to put on b to make it equal x, right? Log base b of x is equal to the exponent that b needs to become x, okay? It's essentially saying the number that we can raise b to the power of and get an answer of x. So for example, log base 4 of 16 is equal to something, right? It's saying what number could we raise 4 to the power of and get an answer of 16? What number could we raise 4 to the power of and get 16? So therefore, log base 4 of 16, right? What we're saying is 4 to what power equals 16? And whatever that power is, that is what log base 4 of 16 is equal to. So the answer is 2, right? 4 squared would equal 16. And so log base 4 of 16 and 2 are the same thing. They're the same number. They're equivalent, right? Let's try this out. Determine the value of each expression. So it's just saying, all this is saying, log base 2 of 8 is saying 2 to what power equals 8, right? And whatever that power is, this is equivalent to that. So what we're saying, again, 2 to the power of what would give us 8, right? Well, the answer is 3. 2 to the power of 3 would equal 8. So log base 2 of 8 is just 3, right? It's equivalent to 3. Okay? All right, same thing here. They didn't write in a base, so what does that mean our base is? Our base is 10. So log of 100 is just going to be equivalent to the exponent we would have to put on 10 to get an answer of 100. So what is that exponent? 10 to the power of what would equal 100? It's 2, right? 10 squared would be 100. So this just equals 2. Log of 100 is 2. Try it out. If you can find the log button on your calculator is defaults to base 10. So that's what that log button on your calculator does. It takes log base 10. Try it out. Do log of 100 and press enter. It's going to say 2 because 10 to the power of 2 would equal 100. Okay, let's try this one out. 5 to the power of what would equal 5? Well, 1, right? 5 to the power of 1 would equal 5. Right? Again, all this is saying, what is log base 5 of 5 equal to? Whatever exponent we could raise 5 to and get an answer of 5, right? This to the power of this equals this. So our exponent is just 1. The answer is 1. Log base 5 of 5 equals 1. Okay. Ooh, this is an interesting one. 6 to the power of what equals 1? What would we have to raise 6 to the power of to get an answer of 1? Well, the only thing we can raise, some number to and get an answer of 1 is 0, right? 6 to the power of what equals 1? The only thing that's going to work is 0. So log base 6 of 1 is just the same thing as 0. All right. Now, remembering these ideas, kind of what we've talked about here, remembering that it's just equivalent to, that exponential relationship, helps us understand what I've been saying. I promise we'll talk about it later. Okay, now we're going to talk about it. Why can our base and argument never be negative? And why can't the base be 0 or 1? Well, if we think about this, if the base could be negative, then we could write things like log base negative 2 of a equals 1/2. Right? I mean, that's totally possible, which could be rewritten as negative 2 to the power of 1/2 equals a, right? Negative 2 to the power of 1/2 equals a. You might be saying, what's the big deal? But negative 2 to the power of 1/2 is the square root. We'd be taking the square root of a negative, right? I mean, even just more generally speaking, remember when we were doing exponentials, we couldn't have, when we had ac to the power of x, we couldn't have c be negative either, because this just didn't become a very well-defined function, right? When x is even, this is going to be positive, but when x is odd, this is going to be negative, and that's not even getting into what about in between, like what about when it's a fraction, then you're taking the square root of a negative, which isn't okay, right? And so it's the same logic here, because a logarithmic relationship is an exponential relationship just expressed in a different way, right? If x is 0, this becomes 1, but if x is 1/2, we're taking the square root of a negative, and that's not allowed. And so that's why our base can't be negative, just like it couldn't be negative in an exponential, okay? Now, since the base can't be negative, there's no way to get a negative argument either, right? Because again, if we have a positive b, right, if I've got, log base b of a equals x, well, no matter what b is, it's positive, right? It can't be negative. So there's no way to raise a positive number to any power and end up with a negative answer, right? Take a positive number and raise it to whatever power you want. It's still going to give you a positive result. And so our argument there, the a, it just can't be negative. There's no way for it to come out as being negative. So taking the log of a negative number doesn't really make sense. If you try it on your calculator, log of, -10, you're going to get an error. It's going to tell you it's a non-real answer, okay? So if b is positive, raising it to any power will still be positive. Just for example, log base 2 of -8 makes no sense, because 2 to the power of what would equal -8? Well, nothing, right? There's no exponent that answers this question. 2 to the power of something equals -8. Makes no sense. There's no exponent we could raise 2 to and get -8 as a result, okay? Why can't the base be 0 or 1? Well, if we think about it, 0 to the power of anything is still 0, and 1 to the power of anything is still 1. So if, for example, I tried to ask you what log base 0 of 5 was equivalent to, you'd be stumped, right? Because again, 0 to the power of what equals 5? Well, nothing, right? 0 to the power of anything is going to be 0. There's no exponent we can raise 0 to and get an answer of 5. It's the same problem for log base 1 of 5, right? 1 to the power of anything is still just going to be 1. So how could log base 1 of anything, of 5, be real, right? It can't be. There's nothing we could raise 1 to the power of and get a result of 5. Okay, is it possible to technically write true statements? I guess so. You could say log base 1 of 1, but that's not very useful, right? We can't do anything other than say this, 1 to the power of anything is 1. And then you can see the problem here is, what is this equal to? Because it could be equal to anything. Because 1 to the power of anything is 1. Right? So this doesn't have a well-defined answer. It's undefined, right? 1 to the power of, we have no way to say what log base 1 of 1 is equivalent to, because it could be anything. 1 to the power of anything would equal 1, right? Same if I tried to say log base 0 of 0. 0 to the power of anything is 0, so this doesn't actually mean anything, right? This could be a billion, a trillion, 1,000, -100. 0 to the power of that would equal 0. So it doesn't have a well-defined value, because again, 0 to the power of anything would be 0. 1 to the power of anything would be 1. And so we can't say that the base is 0 or 1, because it just doesn't work, right? 0 to the power of anything is just going to be 0. It can never be 5, for example. Okay? So that is why we kind of have those quote-unquote rules. We can't have a negative argument or a negative base. We also can't have the base being 0 or 1. Anything else is fair game. All right, go ahead and try these out. They're asking you to use that definition of a logarithm to evaluate these. Okay, so again, what is log base 5 of 125 equal to? Well, ask yourself, what exponent would 5 need to be raised to in order to become 125? And that's what this is equivalent to, right? This to the power of whatever this equals is 125. All right, try those out. You can do some more practice if you're wanting to really get it down. And then when you're feeling good, come on back and we'll move on to looking at some basic log properties. So before we look at some basic log properties, because they're actually very closely related, they're kind of just like the logarithm version of the exponent properties or the exponent laws, okay? We're going to do a quick reminder of our exponent laws. We've seen these, many times in our math courses, but let's just do a quick refresher because, again, the log laws are very closely related to them, or the log properties, I should say, are very closely related to them, okay? So The first one up is the product of powers. That just says if you have, a to the power of m times a to the power of n, where a just represents some number, right? Any number, then you can add those exponents, okay? Just says when two powers with the same base are multiplied together, it's equivalent to that base with the exponents added. And just some examples here to show like, oh yeah, that makes sense. It's not like a magical rule to follow. I don't recommend memorizing these. You probably have them kind of committed to your memory, but understanding them makes it so we don't really need to memorize. We can kind of just produce it and see why it makes sense, right? Because look, x squared times x cubed, for example. This law tells us that that's equivalent to x to the power of 5. But that makes a ton of sense because x squared is just x times x. And we're multiplying that by x cubed, which is x times x times x. So what are we doing? X times x, 2 times x, 3 times, x 4 times, x 5 times, right? X squared times x cubed is x times itself twice times x times itself 3 times, for a total of x to the power of 5, which is why we can add them. The quotient of powers, very similar, except it's dealing with division instead of multiplication. So if we have a to the power of m over a to the power of n, the quotient of powers exponent law tells us we can do a to the power of m minus n. The numerator exponent, we can subtract the denominator exponent. That's all we're saying there. Two powers with the same base are divided. It's equivalent to that base with the exponents subtracted. Again, why does it make sense? We'll think about x to the power of 5, over x cubed. Exponent laws tell us we could just do 5 minus 3, which is 2. And to be honest, that's usually what we do, right? But just reminding ourselves of why it makes sense here. Look, x to the power of 5 is 5 multiplications of x. X to the power of 3 is 3 multiplications of x. So each division by a factor of x is going to end up canceling out with one of these. So we have x to the power of 5, but we got to take 1 away. Notice what I said, take 1 away. Subtract 1 because it's being divided by a factor of x. Take away another 1, that's 2. Take away another 1, that's 3, right? Leaving us with just x squared. And that's why it makes a ton of sense that we would subtract them, because every multiplication of x in our numerator can be canceled out by a multiplication of x in the denominator. X over x is just 1, right? And so that's why if we have x to the power of 5 over x cubed, we know that it's just going to be equal to x squared, okay? The power of powers one, again, that's just saying if you have a to the power of m, but then that whole thing is being raised to the power of n, we can multiply those two exponents together to get a to the power of mn. When a power is raised to an exponent, it's equivalent to that same base with the exponents multiplied together. Again, not some magic trick. It makes sense when we think about what it's saying, right? So for example, x cubed being squared, what does that mean? It means x cubed times itself, right? X cubed times x cubed, which is just x times x times x times x times x times x, or x to the power of 6, right? And so, yeah, like if we have a power of x, or any number, and we're multiplying it by itself that many times, well, that just means we're going to have that many multiplications of x times itself, right? That got a little confusing. But this is just saying x times x times x times itself, right? If there was a cubed there, it would be x times 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 x. X cubed times itself 3 times in that case. 3 times 3 would be 9, which is what we just counted out, 9 multiplications of x. All right, power of a product, all this is really saying is if you have, a product, AB, two different numbers times each other, AB to the power of m, it's equivalent to splitting those up and saying a to the power of m times b to the power of m. So when a product is raised to an exponent, it's equivalent to each part of the product raised to that exponent. Again, it makes sense. Let's look at, xy cubed. Well, that's just xy times xy times xy. How could we simplify that multiplication out? Well, we could do the x times x times x part, right? And then the y times y times y part. This is equivalent, right? xy, xy, xy is the same as xxx times yyyy, which xxx, that's just x cubed. Yyyy, that's just y cubed, right? This is just x cubed. We've got x has been multiplied by itself 3 times. Y has been multiplied by itself 3 times. So yeah, cubing xy is the same as cubing x and multiplying that by y cubed. Power of a quotient, very similar to power of a product, except it's a quotient. We're dividing instead of multiplying. So it just says a over b to the power of m is the same as a to the m over b to the m. So when a quotient is raised to an exponent, it's equivalent to each part of the quotient, numerator and denominator, raised to that exponent. Again, makes sense. If we have x over y cubed, what's that saying? It's saying x over y times itself 3 times. So that's x over y times x over y times x over y. When we multiply fractions like this, right, x times x times x, that's x to the power of 3, x cubed. Over, multiply the denominators, y times y times y, that's y to the power of 3, y cubed. So yeah, x over y cubed is the same as x cubed over y cubed. Okay, now do we show this all out and have to prove it every time? No, I mean, once we're comfortable enough with the exponent laws, we can kind of just apply the exponent laws, but good to remind ourselves of why the exponent laws aren't just like magic tricks, right? Things to be memorized, because memorizing stuff in math makes math way harder and more confusing, and it makes it seem like a magic set of rules that you can't access, right? It's just taking these relationships and coming up with, oh yeah, we can always just do this, right? So that's what we're doing there. Just reminding ourselves of why these exponent laws make sense. Okay, a few more here. We've kind of talked about these a lot as we go, but let's look at this one. A to the power of 0 equals 1. In fact, well, A represented anything anyway. Anything to the power of 0 is equal to 1. Why? Drawing on the power of a quotient law is kind of helpful, right? When we have, for example, x cubed over x cubed, we know that that equals 1, right? We do. It's something over itself. X cubed divided by itself is going to equal 1. Anything divided by itself equals 1, right? But how do we recognize this as being the same as x to the power of 0? Well, x cubed is just x times x times x over x times x times x, right? Our power of a quotient law says we can look at this as x cubed over x cubed, so we can subtract those two exponents, right? And 3 minus 3 is 0. So x to the power of 0 is just 1, right? Look at these cancellations. X over x is 1, x over x is 1, x over x is 1. So I had x multiplied by itself 3 times, but then divided by x multiplied by itself 3 times. So we had x to the power of 3, but we have to subtract off the 3 because of those divisions as well, leaving us with x to the power of 0. And that's why anything to the power of 0 is 1. Okay? All right. A to the power of 1 over n, these are our fractional exponents, is just the nth root of a. So any number to a power of 1 over n is just the nth root of a. So a fractional exponent is equivalent to taking a root with an index of that fraction's denominator, right? So for example, using our power of a product law here can be helpful to think about it, because like, look at this, x to the power of 1/2 times x to the power of 1/2. Well, our exponent laws tell us we can add those two exponents, right? I've got x to a power times same base to another power. I can just add those. So 1/2 plus 1/2, well, that's 1, right? A half plus a half is 1 whole. So x to the 1/2 times x to the 1/2 is equivalent to x to the power of 1. And x to the power of 1 is just x. So what we're saying here is if I multiply x to the power of 1/2 by itself, I get x. Well, that's just the definition of the square root of x, right? The number that if I multiply it by itself gives me x. That's the square root of x, right? What's the square root of 4? It's 2. Why? Because 2 times itself gives me 4, right? So if x to the 1/2 times itself gives me x, then x to the 1/2 must be the square root of x, right? X to the 1/2 times itself is equivalent to x, so it must be the square root of x. That's what it is, okay? Let's just take this a step further. What about, here, let's put in an actual number. 4 to the power of 1/3 times 4 to the power of 1/3 times 4 to the power of 1/3. Our exponent law tells us we can add those up. 4 to the power of 1/3 plus 1/3 plus 1/3. Well, a third plus a third plus a third is 3/3, or 1, right? A whole, 1 whole. So this is 4 to the power of 1, or 4. Now think about what that's saying. When we multiply 4 to the power of 1/3 by itself 3 times, okay, we get 4. So what is 4 to the power of 1/3?
if when we multiply it by itself 3 times, we get 4, it must just be the cube root of 4, right? That's the definition of the cube root. Why is the cube root of 8 2? It's because 2 cubed is 8, right? 2 times 2 times 2 is 8. 2 cubed equals 8, and so 2 is just the cube root of 8, okay? So same logic being applied here. When I multiplied 4 to the power of 1/3 by itself 3 times, we can see that it comes out to equaling 4, right? So 4 to the power of 1/3 has to be equivalent to the cube root of 4. So that is where this one comes from. A to the power of 1 over n is really just the nth root of a. Something to the power of 1/2 is just the square root of that, right? Something to the power of 1/3 is just the cube root of that. To the power of 1/16 is the 16th root of that. Okay. And then this one just kind of takes it and combines it with what if the numerator of our fraction isn't 1? What if we have a to the m over n instead of just a to the 1/nth, a to the 1 over n, okay? But it's really just putting together this with the other exponent that's there, right? So if we have a to the power of m over n, it's the same thing as the nth root of a to the power of m, or alternatively the same thing as the nth root of a, all raised to the power of m. Those are two equivalent things. They always come out to mean the same thing. A fractional exponent is equivalent to taking a root with an index of that fraction's denominator and also raising to the power of that fraction's numerator, okay? So we've already kind of proved the denominator stuff in that previous one, right? We've already seen how the denominator of the exponent is equivalent to a root with that denominator as the index. The power of powers law is helpful to see why we can raise that root to the power of the numerator. Because look, x to the power of 3 over 2, we could just rewrite that if we wanted as x to the power of 1/2 cubed, right? See what I mean? Because we know we could multiply these together. So just as easily, we can unmultiply them to get something equivalent, right? This is the same as x to the power of 1/2 to the power of 3, because we could multiply these exponents together and we'd be back right where we started. So we haven't done anything that's not mathematically sound, right? But x to the power of 1/2 is the square root of x, right? So this is the same as the square root of x being cubed, okay? Alternatively, we could have said this is the same as, if we had x to the 3 over 2, well, that's equivalent to, we could kind of split that up and rewrite 3 over 2 as 3 times 1 over 2, right? X cubed to the power of 1/2. Well, x cubed is x cubed, but if we take the square root, we're now left with the square root of x cubed. So these two are equivalent. The square root of x cubed is the same as the square root of x cubed. The square root of x being cubed is the same thing as the square root of x being cubed. Okay, those are equivalent expressions. All right, and the last one here, just the negative exponent one. Again, we've talked about this, but a over b to the power of negative m is the same thing as b over a to the positive m. And so all that's saying is that a base raised to a negative exponent is equivalent to the reciprocal of the base raised to that exponent, but positive, right? Raised to the positive version of that exponent. Because again, that negative exponent actually means dividing by it that many times, right? And since dividing by a fraction, so dividing by a over b, is the same as multiplying by its reciprocal, so dividing by a over b is the same as multiplying by b over a, that's all we're really doing there, okay? This helps us explain why. Again, if we had x cubed over x to the 4th, we know that we can subtract those exponents, so we kind of know it's equal to x to the negative 1, right? Here's the logic, though, of why we can see that, right? Because x and x would cancel, x and x would cancel, x and x would cancel. And notice what we're left with. We're left with 1 over x, right? I shouldn't say cancel. Really what we mean when we say cancel is it's equal to 1. So this is a 1, this is a 1, this is a 1, and then I've still got an x in my denominator. So I'm left with 1 over x, right? But compare that to what our exponent laws would tell us. X to the power of 3 over x to the power of 4 is the same as x to the power of 3 minus 4, which is just x to the negative 1. And we've already seen that that gives us 1 over x up here, right? We did the same thing here, So x to the negative 1 is the same as 1 over x to the power of 1. Okay, so little reminder of some exponent stuff. Now let's look at these are very closely related. They're like the logarithm versions of the same idea. Some basic properties of logs. Let's take a look. All right, so like I said, we're going to look here at some simple properties of logs that we can take advantage of. In the next lesson, we're going to see more like what's the, log version of this stuff, but we will you'll see the connections here a little bit. We'll also see some more in-depth log laws in the next lesson. This one is really just looking at some basic properties of logs, okay? Again, don't forget, by definition, log base b of x, it just means the number that we can raise b to the power of and get a result of x. So with that in mind, let's take a look at some simple log properties, okay? And the first one here is just when we have an argument of 1. Notice b could be anything, right? It doesn't matter what b is. If you have log base anything of 1, that's just equivalent to 0. Log base anything of 1 is 0. No matter what the base is, the log of 1 is 0. Why does that make sense? Well, because anything to the power of 0 equals 1, right? We talked about that up here. Anything to the power of 0 equals 1. And what this is saying is that b, whatever b is, to the power of 0 equals what, right? So if we just think about log base b of 1, right? B to the power of what equals 1? Well, it has to be 0, right? Log base b of 1 is just saying what power could we raise b to and get a result of 1? And 0 is the only choice there. That's the only thing we can raise something to the power of and get an answer of 1. It's 0. So the reason why anything to the power of 0 is 1, I won't go into it here again because we just talked about, right? But it's just that quotient of powers law, right? That kind of stuff we talked about there, okay? All right, log base b of b, meaning that if we take the log of an argument with a base that is the same as the argument, the result is always 1. So again, notice here, doesn't matter what b is, if we have log base b of b, maybe it's log base 2 of 2 or log base 5 of 5, the result is always going to be 1. It's always equivalent to 1. Well, again, that just makes sense because if we raised b to some power and we got a result of b, that power had to be 1, right? So the only power you can raise a base to and not change it is 1, right? If I raised 2 to some power and the result is 2, the power I must have raised it to had to be 1. 2 to the power of 1 equals 2. 2 to the power of anything else would not equal 2, right? And that's all log base b of b is saying. It's just equivalent to what power we would have to raise b to and get an answer of b. Well, the only option is 1. That's the only thing that could work. What power could we raise b to and get a result of b? It's got to be 1, okay? All right, this one may be a little less obvious than those first two at first, but it makes sense once we think about it. If we take the log of a power where the base of the log is the same as the base of the power, it's just equivalent to the exponent of the power we're taking the log of. That's a lot of words. All it's saying is that if we take log base b of b to the k, it's just equivalent to k. The result is k. This makes sense just when you look at the relationship, right? B to the power of k equals b to the power of k, right? This to the power of this equals this. So that's why, for example, if I had log base 2 of 2 cubed, I can know right off the bat that that's just the same thing as 3. Because what we're saying is 2 to the power of what would equal 2 to the power of 3? Well, obviously it's 3, right? That's what that would have to be. So log base b of b to the k is saying, what power could we raise b to and get a result of b to the k? Well, it's got to be k, right? Log base 4 of 4 to the power of 2, I can tell right away that it's 2. The answer is 2, or this is equivalent to 2 anyway, right? Log base x of x cubed, the answer is 3. Doesn't matter what x is, because x to the power of what equals x to the power of 3? Well, it's got to be 3, right? Log base x of x cubed has to be 3. Okay, This one is probably the least obvious of them on the surface level. It seems a little weird at first, but once you think about it a bit, it does make sense here, okay? So if we have b to the power of log base b of k, the answer, or what that's equivalent to, I should say, is just k. This is saying the same thing as just saying k. That one might be a little less obvious, but it actually is a pretty simple idea once we break it down. If a base is raised to the power of a log with the same base, then that expression is just equivalent to the argument of that log. Okay, so notice here I have b to the power of a log base b. Okay, so b is being raised to a log with a base of b, and the argument is k, and it's saying that just comes out to equal k. Why does this make sense? Well, log base b of k is just saying what power could we raise b to and get a result of k, right? In other words, log base b of k is just equivalent to the exponent we'd have to raise b to in order to get k as our answer, right? This is just saying b to what power equals k. Well, if that's equivalent to that, log base b of k is the number that we would have to raise b to get an answer of k. And that's exactly what we're doing. We're raising b to that power. We're raising b to the exponent we would have to raise b to in order to get an answer of k, right? So b is being raised to the exponent that we would need to raise b to in order to get an answer of k. Let's just put in some numbers to think about this a little bit. So just to think about it with some numbers, because I know it can be kind of hard when it's all just variables. Here's one where I'm just applying this, property here. So I'm saying 2 is my b, so 2 to the power of log base 2 of 8. And according to this, that should just equal 8, right? b to the log base b of k equals k. So 2 to the log base 2 of 8 should apparently just equal 8. Let's break this down a bit though. Because what is log base 2 of 8? What does it equal? Well, it equals, again, the exponent we'd need to raise 2 to in order to get 8 as our result, right? The exponent that 2 needs to become 8. So look, 2 to the exponent we need to raise 2 to in order to get 8 equals 8, right? This to the power of this equals this. That's all we're saying here. 2 to what power gives us 8, okay? Well, I know we know the answer is 3, right? 2 to the power of 3 would equal 8, okay? But what I'm getting at here is that's kind of the definition of log base 2 of 8. It's the exponent we'd have to raise 2 to in order to get an answer of 8. So think about that. 2 is being raised to the exponent we need to raise 2 to in order to get an answer of 8. We are raising 2 to the power of log base 2, 8. And log base 2, 8 is equivalent to the exponent we need to raise 2 to get an answer of 8. Right? So same thing here. I mean, we can kind of show this, right? 2 to the power of 3 equals 8, obviously, right? But that's why this property works, even if we don't know, like if we don't have numbers in where we could actually figure it out. Because what we're saying here, log base b of k, it's the same idea. It's the exponent we'd raise b to, right? Log base b of k is equal to, I guess I should have written this up here, equal to the exponent we'd need to raise b to get k, right? The exponent b needs to become k. This to the power of this equals this. So log base b of k is just the exponent we'd have to raise b to get an answer of k. Well, that is what we're raising b to here. We have b to the power of the exponent we'd need to raise b to in order to get an answer of k. So we're raising b to the exponent that makes it equal k, right? So that is why this one makes sense. I know that's probably the least intuitive of the bunch, but hopefully once we break it down like that, we can kind of see, right? Just some like an equation version here. We kind of just talked about this, but if you prefer equations instead of an explanation like that, right? Log base b of k equals m. I'm just letting m equal something. So whatever, like b to the power of m equals k, right? It tells us that b to the power of m equals k. But since log base b of k equals m, then b to the log base b of k, what we started with, is really just the same thing as b to the power of m, because log base b of k equals m. And we know that from the exponential, b to the m equals k. So b to the m equals k, but b to the log base b of k also equals b to the m, right? That just means b to the log base b of k also equals k, right? If b to the m equals k, and b to the log base b of k equals b to the m, then by the transitive property, b to the log base b of k must also equal k, right? It's kind of essentially saying this, right? If that's true, then that's true. All right, let's try applying these to see if we can simplify some log expressions. All right, so first one here, we've got log base 6 of 6 over log base x of x to the 4th. Let's see if we can use our basic log properties here, right? Again, not really something to be memorized because we can think about it. So log base 6 of 6, this is equivalent to, right, 6 to the power of what would equal 6? Well, 1, right? Log base 6 of 6 equals 1. We can double check. 6 to the power of 1 equals 6. So this is just 1. So this just equals 1 over, okay, and then look at our denominator. Similar idea, log base x of x to the power of 4. What's that equivalent to? Well, it's equivalent to whatever exponent we would have to put on x to get x to the 4th. So x to the power of what equals x to the power of 4? 4, right? X to the 4th power equals x to the 4th. So this is just the same thing as x, oh, sorry, not x to the 4th, 4, right? Log base x of x to the 4th is just 4. Log base 6 of 6 is just 1. So this whole thing just simplifies to 1 over 4, or 1/4. So this is actually, it just has a numerical value. It's just 1 over 4, 0.25, right? All we used there was this basic log property. Again, notice what I mean? Like, it's not like we said, oh, by this log property. We just kind of thought about it. B to the 1 equals b, right? 6 to the 1 equals 6. So log base 6 of 6 is 1, right? Similarly here, we were using, this log property, but again, we were just kind of thinking about it. B to the power of k would have to equal b to the k. So log base b of b to the k is just k, right? Same thing here. Log base x of x to the power of 4, that's just equal to 4. Because x to the power of 4 equals x to the power of 4. Okay, let's try a slightly more involved one here, but not too much more, to be honest. So 2 to the power of log base 2 of 9. That's kind of the one we were just talking about up here, right? This one. We have 2 to a log base 2. So remember, what this is saying is 2 to the power of what would equal 9. Right? This is the exponent we would have to raise 2 to in order to get an answer of 9. And 2 is being raised to that exponent, right? This is equivalent to whatever power 2 needs to become 9. And we're raising 2 to the power of that. So this must just equal 9. Just going to work my way through them here. 2 to the log base 2 of 9 is just 9. Okay? Whoops, not 2 times, sorry. 2 to the power of log base 2 of 9 equals 9. Okay, let's just keep working our way through here. Log base 4 of 2. So 4 to the power of what would equal 2? Well, 2 is just the square root of 4, right? So 4 to what power would equal 2? 4 to the power of 1/2 would equal 2, right? That's the square root of 4. So this is just log base 4 of 2 really just equals 1/2, right? Double check your work. 4 to the power of 1/2 equals 2. Yeah, it works. Okay, so we'll use that information. And then log base 8 of 1. So 8 to what power would equal 1? 0, right. 8 to the power of 0 equals 1. So log base 8 of 1 is just equivalent to 0, right? The only number I can raise something to the power of and get an answer of 1 is 0. 8 to the power of 0 equals 1. So really, this is just saying, right, we have 2 to the log base 2 of 9 minus log base 4 of 2 plus log base 8 of 1. But we've worked out that this is just equivalent to 9 minus 1/2 plus 0. So it's just 9 minus 1/2. Getting a common denominator, multiply 9 by 2 over 2 so that it's a fraction over 9, right? 18 over 2 is the same as 9 minus 1 over 2. This just equals 17 over 2, right? Or 8.5 if you like, but I think a fraction is better anyway. So that thing just simplified to 17 over 2, just by using what a log is really saying. All right, so there's our little how logs work and working with logs portion of our lesson. The kind of going to switch gears here now in the next part of our lesson and start talking about logarithmic functions, saying y equals stuff that involves a log and thinking about its graphs. Okay, so remember what we talked about at the very beginning of this lesson, right? A logarithmic function is the inverse of an exponential function, right? Logs and exponentials are inverses of each other. So as we learned in the first unit, this means we can think of a logarithmic function. Remember, how did we find the inverse? We essentially switch x and y, right? Meaning that if a log function is the inverse of an exponential function, we should be able to go from exponential to a logarithm by switching x and y for an exponential function. So if we had the exponential function, y equals 2 to the x, that's what we talked about in the previous lesson, right? Functions like that. Then its inverse would be, well, switch x and y. So if y equals 2 to the x, then x equals 2 to the y, okay? But to graph this, or at least for most of our functions, right, we often have things in the form y equals stuff, not x equals stuff, because y is the dependent variable. It's the output. So to graph it, to write it in our function notation that we're comfortable with, we'd need to isolate y so that we could think about y equals stuff for the graph, right? So writing this in its logarithmic form, right now, it's not like that, right? Remember what I said, when we have the thing we want to isolate in the exponent, the only way to deal with that is using logarithms, right? No operation can get y out of this exponent except bringing logarithms into the mix. So let's convert x equals 2 to the power of y into its logarithmic form. So again, look here. We're saying 2 to the power of y equals x, right? So whenever we have log base b of a equals, I'm just going to say c, right? This to the power of this equals this. We're trying to say this to the power of this equals this. 2 to the y equals x. So log base 2 of something equals y, right? Look what we're saying. 2 to the power of y equals x. And there we go. This is a function now where we've got our output, y is equal to log base 2 of x. There we go. So we took an exponential, took its inverse, and then isolated y by converting to the logarithmic form. And this is why a y equals log base 2 of x is the inverse function of y equals 2 to the power of x. It's the result of swapping x and y and isolating y by converting to logarithmic form, okay? And now we could graph this. So these are the graphs of y equals 2 to the x. This is what we were talking about yesterday, right? Or in the previous lesson. Every single value of every single value of y is just equal to 2 to that value of x, right? Wherever we are. So like when x is 0, y is 1, because 2 to the 0 is 1. When x is 2, y is 4, because 2 to the power of 2 is 4, okay? Here we have y equals log base 2 of x. Now, I know this might be a little bit less intuitive to think about. So often students will say to me, yeah, but like I don't know what log base 2 of 3 is off the top of my head, right? Don't be scared when you're working with these logarithms. Sometimes it can be a little bit nice to convert or at least think about what it's saying exponentially, right? So this is just saying 2 to the y equals x. It feels a little bit backwards because you're used to putting in x's and seeing what y is, and that is still what we're doing for this function, but you can kind of use it to make sense of the graph a little bit more here, right? So this is saying, like, for example, when y is 0, x will be 1. When y is 0, sure enough, x is 1, right? We see that point on our graph. X is 1 when y is 0, right? Or when y is 2, x will be 4. Sure enough, 4, 2, when x is 4, that tells us that our y will be 2, right? 2 to the power of 2 equals 4, okay? So notice it's still the same thing. It's still a graph. And the key takeaway here, or one of them anyway, is look, does this look familiar, right? We said that logs are the inverses of exponentials. Doesn't this look like it's been reflected in the line y equals x, right? Note that the graph of y equals log base 2 of x is a reflection of y equals 2 to the x across the line y equals x, which is exactly what we would expect for inverse functions. Remember that back in Unit 1, right? When we swap x and y, it's the same as reflecting in the line y equals x. It's taking the inverse, okay? So again, like I said, are you sick of me saying this yet, right? You're probably pretty used to the kind of format of Math 30 at this point. We introduce some new functions, and then we think about transforming them, okay? So we are soon going to think about transforming logarithmic graphs. But before we do, let's get to know some key features of a basic logarithmic functions graph, right? Y equals log base b of x. I'm going to use, because we need to pick a b, otherwise, what are we doing? We have to pick some kind of b. I'm going to use y equals log base 2 of x as the example graph for us to think about, okay? So this is the graph of y equals log base 2 of x. Again, sometimes it can be a little bit more helpful, or at least a little more intuitive, to think about it in its exponential form. But you can see here, again, when all we're doing is this, right? 2 to the power of y equals x, or y equals log base 2 of x. This is really the function, but this can be helpful to see where some of our points are coming from, or it can be helpful to get some points when we're graphing. Again, right? Look, when x is 2, y is 1, because 2 to the power of 1 equals 2. So when x is 2, y is 1, because 2 is equal to 2 to the power of 1. Sorry, I mixed up myself there, right? Or when y is 4, our x is 2, because 2, whoops, sorry, nope, I have that backwards. When y is 2, x is 4, whoopsies, right? Because 2 to the power of y, so 2 to the power of 2 equals 4, okay? So let's think about range and domain, okay? So y equals log base b of x is equivalent to, don't forget, b to the y equals x, right? This to the power of this equals this, okay? Now, much like with exponential functions, we can raise a number to any exponent, right? So the range of any logarithmic function is always just going to be y is an element of the real numbers, right? We're allowed to raise to any exponent. We saw that in a previous lesson with exponential functions. They had a domain. If I have y equals b to the x, their domain was all real numbers. Well, this makes a lot of sense because remember, when we take the inverse, we're swapping x and y, and therefore we're swapping domain and range. So since exponentials had a domain of all real numbers, it makes sense that logarithms would have a range of all real numbers because logarithms are just the inverse functions for exponentials, right? They swap x and y, so they swap domain and range. Okay, now you might recall that exponential functions had horizontal asymptotes. So since logarithms are inverse functions of exponentials, you might predict that they would have vertical asymptotes instead of horizontal because x and y are swapped, and you would be correct to think that. So remember, x can't be 0 in y equals log base b of x, right? Because b to the power of nothing is ever 0, okay? So another way to think about it, like I just said, is its exponential form. Is there any power, y could be, that would make x equals 0 in b to the power of y equals x? No, right? Even if we make y negative a billion, x will never actually be 0. It'll be tiny, but it won't be 0. So in this example here, as y approaches negative infinity, x does get closer and closer to 0, but it never actually reaches it, right? Even if we have b, or let's just put in a number, right? 2 to the negative 1 billion. This equals 1 over 2 to the 1 billion, which is tiny, but it's still not 0. So as y goes off to negative infinity in this equation, which is just the exponential form of this equation, x approaches 0 but doesn't reach it. Hey, that's just the definition of a vertical asymptote. We're going to have a vertical asymptote at x equals 0. We also know that the base b can't be negative, right? And from the equation as well, there's no way to make x negative in b to the power of y equals x, right? If b is positive, no matter what y is, x is going to come out as being positive, okay? So putting these ideas together, the domain for y equals log base b of x is all values of x such that x is greater than 0. Sound familiar? Remember, the range for our base exponential functions were that y had to be greater than 0. Again, this can all be changed by transformations, especially horizontal translations. That's going to change where our vertical asymptote is. But just thinking about like the base one, y equals log base 2 of x, right? For example, this is the same as 2 to the y equals x. There's no way for this to make x negative, and there's no way to make it 0. So the domain is just the set of all x's such that x is greater than 0. Now again, what we're really doing is still inputting x's, but the exponential form can be a little more intuitive for thinking about what are we allowed to put in for x, okay? So here's some showing that we can change where that asymptote is with some horizontal translations. I should mention too, or reflections. That can also change our domain. Much like a vertical reflection could change our domain for an exponential function. Okay, a horizontal reflection can change our domain for a horizontal reflection. Oh, wait, for a logarithmic function. Okay, so looking here, y equals log base 2 of x minus 2, right? This is actually just a horizontal translation. That just means we have an h of 2. We'll look at that in a moment here, okay? But you can see it's like y equals log base 2 of x if I replaced x with x minus 2. So look where our vertical asymptote is now. Instead of being at 0, x equals 0, it's at x equals 2. Vertical asymptote at x equals 2. Starting from x equals 0, it's been translated 2 to the right. Okay, our whole graph has been translated 2 to the right. And so now it approaches 2 as y goes to negative infinity, right? Again, the exponential form can be helpful here. If I have y equals log base 2 of x minus 2, this is really saying the same thing as 2 to the power of y equals x minus 2. And therefore, 2 to the power of y, just add 2 to the both sides, equals x. And now if you imagine y going to infinity or negative infinity, right? Well, if y goes to negative infinity, this just approaches 0, and therefore x approaches 0 plus 2, or 2, right? So it checks out with the equation as well. This one, y equals log base 2 of negative x, we can see that's just replacing x with negative x. That just means b is negative 1. So we've reflected across y-axis. That's kind of what we would predict. It should look like that, right? Going from y equals log base 2 of x, like this. If I reflect it across the x-axis, y equals log base 2 of negative x, it's going to end up looking like that, okay? And so that does affect our domain, because now it's the set of all x's such that x is less than the vertical asymptote, instead of the set of all x's such that x is greater than the vertical asymptote. Doesn't that sound familiar from the previous lesson with the exponential functions, right? Remember, a vertical reflection could change it so that y was less than the asymptote, right? Now a horizontal reflection can change it so that x is less than the vertical asymptote. All of those things I just said are just kind of swapping x and y, inversing, which is what we do when we go from an exponential to a logarithmic function. Okay, and again, the equation can back us up here, because really, what is this saying in exponential form? It's saying 2 to the power of y equals negative x. Solving for x, it's just saying negative 2 to the power of y equals x. And so now this, right, this is now going as y goes down to negative infinity, as y goes down to, or sorry, as x, sorry about that, video kind of froze up on me there. All I was saying there was that, again, like as y goes down to negative infinity, right, x is still approaching 0 for this example here, but it's going to be negative, right? When y is negative a billion, this is a tiny number, but it's a tiny negative number because of that negative out front. So it makes sense that, right, the graph looks like this, and our domain is such that x is less than the vertical asymptote. Okay, so therefore the domain for any logarithmic function is always x must be greater than h or x must be less than h, with the vertical asymptote being directly at x equals h, right? Starting from a vertical asymptote of x equals 0, we translate it to the right or to the left by h units. Okay, and then it's just a matter of whether there's been a horizontal reflection or not that tells us if it's going to be greater than that vertical asymptote or less than that vertical asymptote. That's all the stuff we talked about yesterday with the exponential functions, except swap horizontal and vertical, swap x and y, swap domain and range, right? The domain and range, everything we said it all yesterday, except we reversed where we were talking about it. Everything I said about range today, I said about the domain in the exponential functions lesson. Everything I'm saying about, I forget which one I said, right? But they've just been flipped compared to what we learned for exponential functions. This makes sense because logarithmic functions are just inverses of exponential functions, as we saw at the very beginning, right? Y equals log base 2 of x is just the inverse of y equals 2 to the x. Okay, so some key points to think about as we transform these. All basic logarithmic functions of the form y equals log base b of x, whatever b is, will pass through 1, 0 and b, 1. These points make sense when we remember the exponential form, right? When we remember that y equals log base b of x is really saying the same thing as b to the y equals x, because this to the power of this equals this, right? So when y is 0, we have b to the 0 equals x. And therefore, what's x? Well, it's 1. No matter what b is, x will be 1, because anything to the power of 0 is 1. So 1, 0 will be a point on the graph. Again, these can be changed by transformations, but for the base function, like we always kind of do here, a base function, and then we can compare to how the one we're actually dealing with looks different, and that can tell us about its equation or its graph, okay? If y is 1, then we have b to the power of 1 equals x, right? B to the power of 1 when y is 1. And therefore, x is just whatever b is. So b1 is a point on the graph, right? Look here. Y equals log base 2 of x. When y is 1, x is 2, right? 2 is our b there. So it passes through those 2 points we said. It goes through 2, 1, that's our b1, and it goes through the point 1, 0. When y is 0, x is 1, because 2 to the power of 0 equals 1. Okay, so these key points can be pretty helpful when sketching a graph. Of course, they can be moved by transformations, but their new locations can actually be really helpful for thinking about what those transformations must have been, right? And therefore what the equation must be, or vice versa. Given the equation, you can use those points to transform them according to the equation and then see where they end up now to help you graph your function. So remember, this is one of the key tips I kind of give students when dealing with these logarithmic graphs, because I get it. It's not super intuitive to think about the graph of y equals log base 2 of x, but don't forget, you can always convert a logarithmic function to its exponential form in order to more easily find some points for guiding your graph sketch, right? For example, can we determine 3 points that would lie on the graph of y equals log base 2 of x plus 1? Let's convert it to its exponential form, right? So be careful. We can't just do it right off the bat because it's not in the correct, like we don't have the log isolated, right? I can't say the sentence. 2 to the power of y equals x, but I'm ignoring the plus 1. How do I fix that? Isolate the log. So subtract 1 from both sides, we get y minus 1 equals log base 2 of x. And there we go, now I can say it. So this is really just saying the same thing as, right, this to the power of this equals this. So 2 to the power of y minus 1 equals x. And there we go. This is a pretty quick way to just come up with a few points on our graph. For example, it feels kind of wrong because it's almost like we're inputting y's. Again, we're not. It's a logarithmic function. But just for finding some points, we can say, okay, what about when y is 0? This is 2 to the 0 minus 1 equals x. So that's 2 to the negative 1 is x, or 1 over 2 is x. So when y is 0, x is 1/2. So 1/2, 0 is on the graph, right? There's 1 point, okay? What about when y is 1? We would have 2 to the power of 1 minus 1 equals x. 2 to the power of 0 equals x, so therefore 1 equals x. So when x is 1, y is 1, right? We put in 1 for y, found that that meant x had to be 1. So 1, 1 is on the graph. Okay, see what I'm doing? We're just getting some points. Sometimes students are like, I don't even know how to find a point on a log graph, right? And I tell them, well, just like always, right? An equation can tell you when x is this, y will be that, right? And it's a little easier to do these sometimes with the exponential form, okay? It doesn't have to be, but often that can be a little easier to think about. So what about when y is 2? We'd have 2 to the power of 2 minus 1 equals x. So 2 to the power of 1 equals x. So 2 equals x. So there's another point, right? We made y equal 2, and we found that that meant x must have been 2. So 2, 2 is another point on our graph, right? And we could keep going. We could do 2 to the power of 3 minus 1 is x for this equation. So 2 squared equals x. So 4 equals x. So another point on our graph is that when x is 4, y is 3, right? And onward and onward. All right. Now that we've thought a little bit about the graph of a base logarithmic function, let's think about messing with it, okay? So again, you're probably sick of hearing me say this, but it's because it's the same thing. It's the same skills. Everything we did in Unit 1 for transformations also applies to logarithmic functions, okay? So I'll go really fast through this because we've seen it a million times now, but A causes a vertical stretch by a factor of A, vertical reflection if A is negative. B, horizontal stretch by a factor of 1 over B, because x isn't isolated, and a horizontal reflection across the y-axis if B is negative. Okay, K, vertical translation, K units up if K is positive, or K units down if K is negative. H causes a horizontal translation, H units right if H is positive, or H units left if H is negative. Right? We've got our function notation that acts like instructions on how to transform the equation. We've got our mapping notation that's like instructions on how to transform an individual point. Okay, it tells you what you're actually going to do to each x and y. And so we can apply all of these transformations to the graph of y equals log base c of x2. You might be saying, why did you switch that to a c? I'm just switching the letter used for the base to c just to avoid confusion with the horizontal stretch, b. To be honest, I could have been using c this whole time. B is just the most common one used. Not actually sure why. So I wanted to be consistent with what you're most likely to see in like a video or something like that, okay, or a textbook. But I'm just swapping it out for a C so that we don't mix it up with the B that's the horizontal stretch, okay? And these transformations work the exact same way as they did in Unit 1. Okay, in this way, we can pretty much think of the graph of any logarithmic function as being like y equals log base c of x, but just having been transformed in certain ways, giving us this. Now, once again, this is not on your formula sheet, but it doesn't really need to be because all it's doing is taking this general function notation, right, the instructions for how to transform any f of x, and applying it to the base y equals log c of x equation. Okay, so I'll show you how we got that. So again, in general, we've got y equals, to transform any f of x, if we want to transform it, this tells us how to do it. That's all this is doing. It's saying take f of x, and instead of doing f of x, do f of b times x minus h if you want to horizontally stretch or horizontally translate it. And then multiply that by a if you want a vertical stretch or reflection, and add k if you want a vertical translation, right? So if we take those instructions and we apply them to this, y equals log base c of x, okay? Well, again, kind of two parts, right? Replace x with b times x minus h. That's kind of step one. So let's do that. Let's figure out what f of b times x minus h is. Well, if f of x is log base c of x, then f of b x minus h is going to be log base c of b times x minus h, right? Replace x with b times x minus h. Notice that's this part there. So that's f of b times x minus h if if our f of x is log base c of x. So overall, right, to transform it, it says first replace x with b times x minus h, and then multiply the result of that by a and add k. So let's do that. I'm going to multiply this by a, and I'm going to add k. And that's where that comes from. So no, it's not on your formula sheet, but the general instructions on how to transform any f of x are on your formula sheet. And so if you're just doing it to this equation, it's the same thing you would have been doing in Unit 1. Replace x with b times x minus h, multiply whatever that is by a, add k to whatever that is, okay? Now, the other thing, just like with exponential functions, we just have to be aware of the value of c as well, because this tells us whether the graph is increasing if c is greater than 1, or decreasing if c is between 0 and 1 as x gets larger, okay? So whether it's going up or down as x gets larger. And all of this information can let us write the equation for a logarithmic function from its graph, or the graph from its equation. Just don't forget our RST, order of operations, right? Reflections and stretches have to become before translations, because reflections and stretches multiply x and y. And multiplications have to come before additions or subtractions, which is what translations do to every x and y point. Okay, let's try out some examples. So we're going to think about these and complete the table, okay? So let's just start out with the top row here. We want to think about what transformations are being performed to the base graph, y equals log base c of x. So for this one, the base graph would be y equals log base 2 of x. Well, it looks like all that we've really got here is an h. What is our h? Our h is negative 1, right? So what kind of transformation does that suggest? A horizontal translation, 1 unit left. Okay? All right. So we will think about this in terms of like transformations. It's always a good way to look at it kind of both, but I'll also kind of think about it in terms of the equation as well, and how that can also tell us where this asymptote should be once we, take apart this log a little bit and think about what it's telling us. So the asymptote, where would a y equals log base 2 of x have an asymptote? Right, it would be at x equals 0. So like normally, right, for y equals log base 2 of x, the vertical asymptote would be at x equals 0. But this has been horizontally translated 1 unit left. But the horizontal translation moves this 1 unit left. So where is it now? It's at x equals negative 1, right? So this is going to have a horizontal, a vertical asymptote at x equals 1. Okay, so that's how we can kind of think about it in terms of transformations. But the equation has our back here too. So off to the side here, I'm just going to kind of convert this to exponential form. Okay, now the log is actually isolated, so I'm ready to go. I can say 2 to the power of y equals x plus 1. And therefore, since we're looking for a vertical asymptote, it would be a good idea, isolate x, and then we can think about,
2 to the y minus 1, just subtracting 1 from both sides there, right? And now we can kind of think about it. As y goes to plus or minus infinity, what does x approach? Well, as y goes to negative infinity, this just approaches 0. So x just approaches 0 minus 1, or negative 1, right? Whoa, sorry, I wrote the wrong thing there. I think I said it right out loud, at least I hope I did, but I didn't actually write in the negative. We moved it 1 unit left. Sorry if that was confusing, that probably was. Okay, right? And that's exactly what we got by thinking about it in terms of transformations. The same thing the equation is now telling us. As y goes down to negative infinity, this approaches 0. 2 to the y approaches 0. So overall, x is approaching 0 minus 1, or negative 1, right? And that's our vertical asymptote at x equals negative 1. X can get closer and closer to negative 1, but it can't reach it. Okay, the key points, remember, for any logarithmic function, the key points are 1, 0, and c, 1, right? That is for y equals log base c of x. Again, because c to the power of 0 equals 1, and c to the power of 1 equals c. So they're normally at, I'm just going to say, without transformations, they would be at 1, 0, and c1, but our c here is 2, right? So that means 2, 1. But this has been transformed. The ht, the horizontal translation, moves these 1 unit left, right? So we're going to have our key points now ending up at, well, 1, 0, if I move that 1 to the left, now it's at 0, 0. And 2, 1, if I move that 1 to the left, it's going to be at 1, 1. So there we go. There's how our key points have kind of been moved. All right, domain and range. Well, again, remember, this is really just saying the same thing as this. So are there any restrictions on what y can be? No, right? Y can be any exponent. We can put anything in as an exponent. So range will be the set of all y's such that y is a real number. Just like the domain for an exponential function was the set of all x's such that x could be any real number. Domain's a little bit more involved, but it's not too bad. We know we have a vertical asymptote at x equals negative 1. So we know our graph will approach negative 1, but not reach it, okay? Now, the only question is, which way does it approach it from? Is x always less than negative 1, or is x always greater than negative 1, okay? Well, to answer that, we need to think about whether it's been reflected across the y-axis or not, right? Are we dealing with a logarithmic function that looks something like this or looks something like this? Well, it's this one, right? It has not been reflected. There is no b, well, there is a b, but it's positive 1, right? So no reflection has occurred. So our domain will be the set of all x's such that x is greater than our vertical asymptote, which is negative 1. And x is an element of the real numbers. And then to sketch it, again, students sometimes say to me, okay, I got like a couple key points, but I can't think of the other ones. So let's put in what we know, okay, and then we'll worry about filling in a few more points just to fill in some gaps if we're not feeling very confident. We know we have a vertical asymptote at x equals negative 1. That alone is huge because now we know that x approaches that line. Okay? All right. Now we also know a couple points that it passes through. We already found those, a few key points. 0, 0, right? And 1, 1 are 2 points that it will pass through. This kind of already gives us an idea because we said that as y goes to negative infinity, x is going to go to negative 1, right? So in other words, it's going to approach that asymptote like that. But to get, maybe a few more points to feel a little more confident, this is where I say, you can always just switch to exponential form and start thinking about some combinations of x and y, right? So we did when y is 0 and when y is 1 already. Let's just try out a few more. We converted to exponential form and found that it was x equals 2 to the y minus 1.
right? So how about when y is 2? When y is 2, this becomes 2 squared minus 1, which is 4 minus 1, which is 3. So that gives us a point. When x is 3, y must be 2. Okay, so 3, 2 is a point on our graph. Okay, might not do too many more points because you can kind of see the shape that's coming out here. What about when x is, I'm going to say when x is, how about, I can't make it -1. How about when x is like -1/2? Might seem a little weird, but it's just going to give us an approximate idea of where some stuff is. So when x is, sorry, not when x is -1/2, I got mixed up there. When y is -1, and there I can make y -1. So I'm going to make y -1 and figure out what x is, right? Well, when y is -1, we've got 2 to the -1, which is 1/2 minus 1. So x will be -1/2 or -0.5, right? There's another point. When x is -0.5, y must be -1. So that gives us a point we can kind of put into our graph. When x is -0.5, y is -1, somewhere around there. And just like we'd predict, right, from here we can kind of just think about the equation. We know that as y goes to -infinity, so as we go down on the y-axis, this approaches 0, so x overall just approaches -1, that vertical asymptote. Gets closer and closer without touching or crossing, right? And as y goes up and up, right, x also goes up and up, kind of has this shape here, right? The inverse of a logarithmic function, or sorry, of an exponential function, which would do something like, something like this. Okay, it's a reflection in the line y equals x. So there we go. We've done a pretty good job of sketching this thing. Okay, what do we do? The few key features, and then to fill in some gaps, we can always just get a few more points. And like I said, it's often easier to get a few more points with these, with the exponential function, or sorry, the exponential form of the logarithmic function, just because we're a little more comfortable with exponentials and we can calculate them a little more intuitively. Okay, let's try the next one here. So definitely some more transformations going on this one. We can see some more parameters. Let's just pick them out. I see an a value. Looks like a is -1. So that tells us a reflection across the x-axis has occurred. I see a b even. I see b is 2, meaning there's been a horizontal stretch by a factor of 1/2. And now I see an h again. No k this time, but there is an h of -2. Okay, so what does that mean? It means there's been a vertical reflection across the x-axis. There's been a horizontal stretch by factor 1/2 about the y-axis. There's been a horizontal translation 2 units to the left. Okay, so let's first just think about this in terms of the transformations, okay? Where will that asymptote be now? Well, again, for y equals log base 2 of x, we would expect it to be at x equals 0. Now, does the reflection change that? Does a vertical reflection change that asymptote? No, right? If we have a, here's roughly what y equals log base 2 of x looks like. If I reflect that vertically, I end up with something like this. Now, it's still got the same asymptote. It's just that it approaches it as y goes to positive infinity instead of as y goes to negative infinity. So the reflection won't change that. Will the horizontal stretch change that? Well, again, no, right? It's at x equals 0. So multiplying our x's by 1/b is not going to change the fact that they still approach 0 as y goes to infinity. So the only thing that can change this, like we said earlier, is a horizontal translation, right? And we do have a horizontal translation, but the horizontal translation moves this 2 units to the left. So if the vertical asymptote started at 0, where's it going to be now? Right, it's going to be at -2. So our vertical asymptote is at x equals -2. Okay, stretch and reflection. Stretch, reflection don't affect this because it's at x equals 0. Now, another way to prove this to ourselves is to write it in the exponential form and see what happens to x as y goes to infinity. Okay, so here we go. I can't quite, be careful, you might think you're able to say it, but you're actually not quite able to say the sentence yet, because if I go 2 to the power of y equals this stuff, I'm ignoring the negative. So let's just divide both sides by -1. This is saying negative y equals log base 2 of 2 times x plus 2. And now we can convert to the exponential form. So this is just saying 2 to the negative y equals 2 times x plus 2. Solving for x, divide both sides by 2. So 2 to the negative y over 2 equals x plus 2. And then subtract 2 from both sides. 2 to the negative y over 2. We could simplify that a bit, but I might just leave it. Doesn't make a huge difference here. Equals x. Okay, now look. As y, think about what we were just saying, right? We just said normally y equals log base 2 of x looks something like that, right? So vertically reflecting it is going to make it look something like that. And then horizontally translating it 2 units to the left, overall, ends up looking something like that, okay? Think about this, okay? We said a vertical asymptote was at x equals -2. So look what happens. As y goes to infinity now, I have like 2 to the power of, negative a billion. That's approaching 0. So this whole side then, as y goes to positive infinity, is approaching 0 minus 2. So x is approaching -2 as y goes to positive infinity. Hey, right? That's what we got. As y goes to positive infinity, x goes to -2. We have a vertical asymptote at x equals -2. Cool, right? Okay, let's get some key points here. And by key points, I mean those 1, 0, and C1. So normally it would be at 1, 0, because again, 2 to the power of 0 equals 1, right? And 2, 1. Because again, 2 to the power of 1 equals 2. And this is, we're comparing to the base function, y equals log base 2 of x. Okay, so we've got to apply all of those transformations, right? There's a few things happening here now. There's a vertical reflection across the x-axis. So what's that going to do? Well, it's going to multiply all of our y's by -1. Right? We take all of our y's and we multiply them by -1, okay? We've got a horizontal stretch by a factor of 1/2. What's that going to do? It's going to take all our x's and multiply them by 1/2, okay? And then we've got a horizontal translation 2 units left, so that's going to take all of our x's and subtract 2 from them, okay? So putting this together into mapping notation, we're going to go from xy into 1/2 x minus 2. That'll be our new x coordinates. And our new y coordinates are just going to be whatever y was, but made negative, because all we're doing to y is vertically reflecting it across the x-axis. So what's that going to do to the point 1, 0? Well, 1, 0 is going to end up at, 1, 0 is going to end up at, we're going to multiply x by 1/2 and subtract 2. So I'm just running out of room here, so I might just kind of do this mentally. So 1/2 of 1 is, 1/2 or 0.5. And then 0.5 minus 2 is -1.5. 0, if I multiply that by -1, is still 0. So there's a point that's going to be on my graph, -1.50. Let's just go ahead and add it in. -1.50. Okay. The other key point, 2, 1, where's that going to end up? Well, I multiply the x by 1/2, so 2 times 1/2 is 1, and then I subtract 2 from it. So -1, right? Oh, sorry, no, 0. No, yeah, -1. My mental math was bad there. 2 times 1/2 is 1, minus 2 is -1. Yeah, that's right. So negative 1 is the new x coordinate. And then 1, right, we go from y to negative y. So 1 becomes negative 1. So there's a point on my graph. When x is negative 1, y is also negative 1. Okay, now let's do the domain and range, and then we'll continue to sketch this thing. Our range, always pretty simple for logarithmic functions. Y is just kind of, we can think of it as an exponent here. So it's the set of all y's such that y is any real number, because we can raise a number to any exponent we like. The domain, well, we know that we have an asymptote, right? It's at x equals negative 2. We've just got to think about, is it always greater than that asymptote, or is it always less than that asymptote? Well, has a horizontal reflection occurred to flip our graph across the y-axis? No, it hasn't, right? So it should look, rough horizontally anyway. It kind of does the same thing as this. It's always greater than the asymptote. So our domain will be the set of all x's such that x is greater than negative 2. X is an element of the reals. Okay, and then we can always just use the equation to get a few more points. Like I said, it's often a little bit easier in exponential form. It's just a little more intuitive to do the calculations. Okay, we already know when y is 0 and when y is negative 1. Sorry, I think the video got cut off there, but like I said, was saying anyway, we already know the points when y is 0, when y is negative 1. So let's just, essentially create a table of values here to help ourselves graph a little bit more, right? We've got the equation, right? Let's just put in some y's we don't know, and that can give us a few more points to maybe help us fill in the gaps a bit. So the equation is 2 to the negative y over 2 minus 2 is equal to x. So let's just figure out some x's, right? And some y's, some points that go on our graph. So when, like, y is positive 1, let's say, we've got 2 to the negative 1 over 2 minus 2 will equal x. So we can figure out what x gives us a y of negative 1. Well, 2 to the negative 1, that's 1 over 2. And then we're dividing that by 2. Minus 2 equals x. So this might be some decimal, but that's okay. 1 over 2 divided by 2, that's the same as 1 over 2 times 1 over 2, right? 1 over 2 dividing by 2 is the same as multiplying by 1 over 2, just to make this a little easier to think about. So this is 1 over 4 minus 2. So 0.25 minus 2, that's negative 1.75. So that gives us a point, right? We're making a table of values, essentially. Never a bad strategy when you're trying to make a graph. When x is negative 1.75, y will be positive 1, right? There's a point on our graph. When x is negative 1.75, y is positive 1. Obviously this is a pretty rough sketch, but we're getting some points here, okay? How about when y is, I don't know, how about when y is positive, actually no, let's do a negative y. How about when y is negative 2? We haven't looked at that one yet. We would have 2 to the negative 2 over 2 minus 2 would be our x. So 2 to the negative 2, that's 1 over 2 squared over 2. Sorry. I said we were going to make y negative 2, and that is what I meant to do, but I forgot that it was 2 to the negative y to begin with. So this is 2 to the negative. If y is negative 2, we have 2 to the negative negative 2. So that's just 2 to the positive 2 over 2. Okay, 2 squared is 4. So 4 over 2 minus 2 is x. 4 over 2 is 2, and 2 minus 2 is 0. Whoops. 0 is our x. So there's another point, right? We see now that if x is 0, y comes out to be negative 2. When x is 0, y comes out to be negative 2. So there we go. There's another point on our graph. X is 0, y is, right around there, negative 2. Just found the y-intercept. Okay, and you could keep doing this for more and more points, but you can kind of see the shape that this graph is headed, right? Especially knowing the general shape of a logarithmic graph. So let's fill in some of our key features, and then I feel pretty good about sketching the shape of this graph. So we'll put in our vertical asymptote at x equals negative 2. So VA at x equals -2. We know as y goes to positive infinity, our graph just approaches that, so it gets closer and closer without reaching it. And then we know some points that it passes through, and we kind of know that a logarithmic graph looks like that. Okay, and there we go. That is a pretty good sketch of our y equals negative log base 2 of 2 times x plus 2. Right? So the same ideas. I know it's a little tricky at first thinking about these logarithmic graphs, but some strategies to fall back on, right, are the same you've always fallen back on. Asymptotes. Those are a great clue because they let you know what your graph's going to approach, right? Getting a few key points, just making a table of values like you've been doing since like really junior high, right? Make a table of values to get some points to help you plot the graph. Use those key points, think about the transformations, and don't forget, you can always convert a logarithmic form to its exponential, and that's a quick way to just start thinking about, okay, so what happens when y goes up to infinity or negative infinity? And what happens if I make y a certain number, right? That's a free way to get some points. Okay, couple more examples here, and then we are done. So it tells us that in each case below, the graph of y equals g of x, those are the red ones, are obtained by transforming the graphs of f of x equals log base 3 of x. Okay, so the black graph is in both examples, y equals log base 3 of x. For b, the dots indicate corresponding points between f of x and g of x. Okay, so we'll use those probably to think about like stretching and stuff. How did these 2 points become those 2 points? But it wants us to determine the equation of g of x in each case. So this is what we always do, right? Look at our kind of like base graph, and then look at the graph we're actually trying to find the equation of, and see how we could maybe describe this one as like a transformation to this one, right? Because if we can do that, we can write its equation. We just need to take this thing's equation and put in the right a, b, h, k, and we'll have the equation for g of x. So let's take a look. Well, this one actually looks like a fairly simple transformation because I'm noticing the shape of it hasn't really changed. It's really just the location, right? For example, look, like I go here, it's still the same shape, right? Over 2 up 1 is still over 2 up 1. It doesn't look like it's been vertically or horizontally stretched, right? It also doesn't look like it's been horizontally translated. In fact, if I just pick a point on this one, the corresponding point on y equals g of x is always just 1 unit above it, right? The point 1, 0 has become the point 1, 1. The point 3, 1, which we would expect to be on this graph, right? That's that C1 point, 3 to the power of 1 equals 3, okay? So 3, 1 is now at, on g of x, 3, 2, right? They've all just been shifted up on the y-axis by 1. So it honestly looks like our only transformation here is a vertical translation 1 unit up. In other words, we just have a k value of 1. So the equation for g of x is just going to be the equation for f of x plus 1, right? That's just coming from y equals af of bx minus h plus k, which for a logarithmic functions means a log base c of b times x minus h plus k. Well, doesn't look like we really have an a and a b, or we do, but they're just 1, and our h is just 0 because there's no horizontal translation. So this is just going to be g of x is just going to equal the equation for f of x plus 1, right? Plus our k. So g of x is just going to be log base 3 of x plus 1. And there we go. It looks exactly like y equals log base 3 of x, but we've added 1 to every y value, giving us this graph. Haven't changed the shape, we've just changed the location, right? We've slid, is that right? Slid it up by 1. Doesn't sound right. Slided? Well, that sounds even worse. Anyway, it's moved up by 1. Translated 1 upward. All right, let's look at B. Okay, now can we pick up some stuff? One thing I noticed right away is this actually doesn't have the same vertical asymptote, right? Normally, y equals log base 3 of x would have a vertical asymptote at x equals 0, like it does here that we can see. This one, where's its vertical asymptote? Looks like it's at -1, right? This has a vertical asymptote at x equals -1. So how did that happen? Could a stretch do it? Could a reflection do it? I mean, it looks like it has been reflected, but would that, just a reflection, change the asymptote? No, only a horizontal translation. Remember, h directly tells us the vertical asymptote. H must be -1. So all we're doing here, again, is we're just filling this in. Y equals a log base, I'll put in the 3 because that's what our 3 is here, times b of x minus h plus k. Well, one down. We know that h has to be -1, otherwise the vertical asymptote could not be at x equals -1. Okay, the other thing here, they pointed out these corresponding points. So this is kind of interesting because if we look, it's telling us that these are corresponding points. So look, this was, width of 1, height of 1. Just drawing it slightly width of 2, height of 1. Just drawing it slightly below so that you can see it over the x-axis, right? What about this one, though? These two corresponding points, it's telling us that these 2 points are where these 2 points end up after our transformations. Now they've got like a width of 2 still, but a height of 2. So how could we have achieved that? Well, we must have vertically stretched it, right? We've stretched it to kind of make it taller. So the only way for this to happen is if we multiplied all the y values by 2. In other words, a vertical stretch by a factor of 2. So that means a is 2. So there we go. We got a now. 2 down, 2 more to think about. Okay, well, B, we can tell there wasn't a horizontal stretch, right? If these 2 points were corresponding, they're still, on the x-axis, they're still 2 units apart, right? Yes, they're now twice as far apart from each other vertically. That's why there's been a vertical stretch. But horizontally, they're still separated by the same distance. So there hasn't been a horizontal stretch, but it's pretty clear that there's been a horizontal reflection, right? I mean, even look, this point that was at 1, 0 is now at -2, 0, right? So it would have got reflected to -1, and then the horizontal translation would have moved it 1 more to the left, putting it to -2. So it looks like our B is just -1, right? But we got B. So A, it's been reflected across the y-axis, telling us that our B is -1. No stretch, so 1, but reflection, so -1. Okay, and what about K? Is there a K? Well, I don't think so, right? Because look, vertically stretching this point, for example, by multiplying it by 2, would put it to a y value of 2. And then reflecting it and translating it ends it over here, but it hasn't been translated up or down, right? It has been shifted 1 to the left, right? We would multiply this by 2, the y value by 2, then multiply its x value by -1 to put it here, and then horizontally translate it 1 unit left to end it up there. But it hasn't been moved up or down. It's probably even easier to think about with this one, because this point would be invariant to the vertical stretch, because its y value is 0. So multiply it by a, and it's still at 0. Horizontally reflected across the y-axis, and then translate it 1 left, but no movement up or down. So no vertical translation, so K equals 0, meaning we don't really need to include it in our equation. So we've got our A, it's 2, we've got our B, it's -1, we've got our H, it's -1, and our K is just 0. So we can write the equation for this by comparing, again, to what log base 3 of x should look like. So y equals, just filling it in now, A is 2, vertical stretch by a factor of 2. Log base 3 of our B is -1, so I'll just write it as negative, because the 1's not going to change much, times x minus h, so x minus h, careful, our h is -1, so that's minus -1, x plus 1 then, plus k, but our k is 0. So there we go. That is the equation of this logarithmic function, right? Pretty cool that just based on looking at the graph, we can write its equation by thinking about how it's like this base graph, but having been messed around with in these ways. Okay, last one for this lesson. It's a good old diploma question, one released from an old diploma. Let's try it out. So again, often a good strategy with these where you're given some information. Sometimes to read the question first doesn't always help, but it never hurts. So the value of the base b to the nearest hundredth is blank. Okay, so we're looking for the value of some base. Aha, there's a base. So the graph of y equals log base b, that's what we're trying to find apparently, of x plus c, which is shown below, passes through the points 0, 0, and 3 over 2, 1 over 2. All right, now they gave us the graph, but honestly, I don't know how much they needed to, because this is actually the information we need, right? If we want to actually numerically solve for b, we kind of need this information. The graph could be helpful if they had put some numbers on here, but they didn't. So it might not be the most helpful thing in the world. What it does let us confirm, I suppose, is that like no reflections have occurred. But even then, we kind of knew that anyway because it was y equals log base b of x plus c. There was no negative there, negative there. So I don't know. I don't know how helpful the graph actually is. But this is a very common type of question, right? I mean, you've seen this before. They've given us an equation where we don't know two things. We don't know b and we don't know c, okay? But they've also given us 2 points, which means that 2 times we can put this in as x and put this in as y, and then do it again. Put this in as x and this in as y. And often what ends up happening is that when we do 1 point, that lets us figure out or at least get an expression for b and or c, right? Meaning that maybe when we do this, we can figure out what c is, and then we can use the other point now that we know what c is to figure out the only thing we don't know, b, right? It's like a system of equations. I mean, it is a system of equations. Sure, there's 2 things we don't know, but because we have 2 points, we can build 2 equations. And whenever we have 2 equations and 2 unknowns, that's a solvable system, okay? So I'm going to jump in here. I'm going to use 0, 0. The reason I'm choosing to start with 0, 0, I mean, you could start with this one as well, but can you see my logic there, right? It's nice when things are 0. It's easy to solve equations when we get to put in zeros because some of the equation ends up basically disappearing. So I'm just going to see what happens when I put in 0, 0, right? Because remember, any equation, right? Any equation, what the points on its graph are doing, what those points are, they're all points that satisfy the equation. That's why they're points on its graph, right? 0, 0 is on this equation's graph because the combination of x being 0 and y being 0 makes this equation true. So knowing that, I can start to think about, all right, well, what would b and c need to be if for y equals log base b of x plus c, apparently, when y is 0, x is 0, right? See what I mean? We can now start kind of thinking about what would b and c have to be if 0, 0 is on this equation's graph. Well, look, I think this was a good choice to start with 0, 0, because now I've got 0 equals log base b of 0 plus c, which is just c. And now we don't know b, that's true, but this is just saying that b to the power of 0 equals c. So converting to exponential form, this is just saying b to the power of 0 equals c. And so not only do we now have an expression for c that we could, maybe do something with, we can actually figure out what c is, because b to the power of 0, anything to the power of 0, is 1. So it doesn't matter what b is. I mean, it does, because that's what we need to figure out. But for this, it doesn't matter what b is, because anything to the power of 0 is 1. And so if we can show, based on this, that b to the power of 0 equals c, c must be 1. So think about that now. Now we know that c is 1. Can we use that maybe with the other point to figure out what b is? Because if I put in these as x and y now, and I know c, I'll create an equation where the only thing I don't know is b, right? You might be thinking, why not use 0, 0 again? Well, because of this, right? We know this is going to end up here. So while it might give us something true, it's not going to let us figure out b, because whatever b is, we're just putting it to the power of 0, giving us 1. So that doesn't actually tell us what b is, because anything to the power of 0 would have given us 1. So now we can find, right, step 2, now we can find b. So y equals log base b of x plus c, but now we know that c is 1. And so, again, any point on the graph of an equation is just a point that works, that satisfies this equation for x and y. So that means when y is 1/2, that can only happen if x was 3/2 for this equation. And that lets us figure out, well, what would b have had to be then, right? If 1/2 and 3/2 are combinations of y and x that work, what would b have to be? So this means we've got 1/2 equals log base b. Since we're going to the nearest hundredth, I might just work in decimals here. Actually, no, I'll leave it in fractions. Let's not shy away from fractions. So 3/2 plus 1/2, getting a common denominator, 3/2 plus 1, getting a common denominator, multiply 1 by 2/2. So 1/2 equals log base b of 5/2. And then look at this. What's this saying, right? b to the power of 1/2 equals 5/2. And what's b to the 1/2? Well, we know that's just the square root of b, right? In other words, the square root of b is 5/2. So how do I solve for b? Well, I need to undo the square root. So square both sides. We could have done that here as well to get rid of the power of 1/2. Okay. Anyway, that gives me b equals, well, 5/2 squared. That's 5/2 times itself, right? So 5 squared over 2 squared. 5 times 5 over 2 times 2. That's 25/4. So b is 25/4. We found it as a fraction. They wanted it to the nearest hundredth. So that just means, write this fraction as its decimal form, actually divide 25 by 4. And what do you get? You get 6.25 to the nearest hundredth. So the answer to this one would be 6.25. And you could check your work, right? You could make b 6.25. We know c is 1, so try that out and see if you can make these points work out, right? That's a way you could check your work on this question. So on the diploma, we would put in 6.25, and then we'd fully fill in 6, fully fill in the decimal, fully fill in the 2, and fully fill in the 5. And that's how we would record our answer. Alrighty, so that's the last example for the notes. Here is, a suggested practice while this stuff is fresh in your brain, but that's it for this lesson entirely, so you can, work on whatever practice you're wanting to for this lesson. As always, don't be shy, reach out with questions, concerns, anything you're not quite sure about. But there's our introduction to logarithms, and in the next lesson, we'll look at some laws of logarithms and simplifying equations that involve these logs. Alrighty.